Okay, so we're at the middle of chapter 5, and I want to get into some of the content in chapter 6, greenhouse effect. But rather that there is just far too much content, and there's a lot of content that says, well, this is a consideration, but then again, no, because the Earth's climate is so incredibly complicated. So this fits more like it. Let's just have a quick look through the book. Let's go look at the subheadings as we go and have a conversation if we need a conversation. And not a lecture. There's just too much stuff. Plus we've done background. We kind of know stuff. All right, so I'm gonna go back to like 5.9. 5 is a long chapter, and then 6 is also a long chapter. Let's see what we can get through. Also, there's 6 kind of layers into 7 as well, which is an alternate. All right, 5.9 says, hey, if we put new carbon dioxide into the atmosphere, how long does that carbon dioxide stay in the atmosphere before it finds some way out of the atmosphere? What words do we use to pull gas out of the atmosphere?
Is it fixing?
So the process is called fixation.
And it's a sink.
Into a sink, yeah. And if that's, some sinks are temporary. Biomass is temporary. You can take the carbon dioxide out of the atmosphere, turn it into cellulose. That tree lives 100 years. You fixed that carbon dioxide for 100 years, but then that tree dies, decomposes, gives us that carbon dioxide back. The true long-term way of fixing is into the ocean. Fortunately, our ocean surface is huge. How much of the Earth's surface is covered by water? It's not in the book, but
it's like 80%.
it's about 71% of the Earth's surface is covered by water. And of course, that's where solution happens. Solution happens at the surface. Whether it's a solid dissolving in water, can only happen at the surface. Gases dissolve in liquids at the surface, unless you do something dramatic, like in your fish tank, you have a bubbler, and you inject the gas into the body of the liquid. That happens at the surface. Other things that happen at the surface, evaporation. Evaporation happens at the surface. And there's that's going to come up in just a second. Okay, so yeah, we can turn carbon dioxide, if we've got calcium ions, into calcium carbonate. If you had magnesium, you could turn magnesium carbonate also. We know that the sea is full of minerals, right? What's in the sea? What's the obvious one?
Fish and, seashells. But, or is that what
Okay,
you're talking about?
if I'm talking about minerals that are
minerals.
in the
It would
ocean.
be sodium.
Yeah, sodium chloride,
sodium
right? That we harvest as sea salt, and we go, all of this, we can taste the sodium chloride in seawater, or we think we can. Sodium carbonate is not a sink because all sodium salts are soluble. So yes, we can take carbon dioxide, turn it into carbonic acid, H2CO3. We can replace anything in group 1, hydrogen, with any other thing in group 1, sodiums. So I could make a whole bunch of sodium carbonate, but it's always going to stay soluble. So it's never going to precipitate to the bottom of the ocean and take itself out of the cycle. It's always going to be in the biological part of the environment. So we need something that's insoluble. And abundance. So we need something that there's a lot of calcium. The other one would be magnesium. Magnesium carbonate is also a mineral, but not on the level that calcium carbonate is. And we see calcium carbonate in limestone, calcite. If this were a geology class, we'd learn about all the different morphologies of calcium carbonate. Okay. The carbon dioxide gets into the atmosphere by both natural and man-made sources. In taking a look at the book, if we were to pick a percent, and let's just pick the carbon dioxide because it's the poster boy for what a greenhouse gas is. What percentage of the carbon dioxide that gets introduced into the atmosphere each year has a anthropogenic source, a man-made source?
I would say probably it's a very small compared to what you would think it would be.
Yeah. Turns out about 4%.
Yeah.
About 4%. So nature is always putting carbon dioxide into the atmosphere, but it is also always pulling carbon dioxide out of the atmosphere. It's why we had a carbon cycle. It's why it was important to put the carbon cycle up on the board a few days ago and say, our book is talking about gas going out and gas coming in, but it has missed an opportunity to show us at a very simple level that this is all cyclical. If you add up all of the fossil fuels that we're burning and all of the other stuff that we're doing, it's about 4%. It's about 4%. So 96% of the carbon dioxide that is emitted into the atmosphere each year comes from a natural source. Decomposition. It is largely a decomposition pathway. Of course, mammals
Yeah.
breathe out carbon dioxide, but plants thrive in carbon dioxide. They need it to fix that carbon dioxide so that they can have cellulose, which our book consistently is writing as CH2O. It's writing it as just the empirical formula. I would write that as C6H12O6, but again, that's still not cellulose, that's just glucose. But okay. All right, so the framework is, are we getting only about 4% of it is man-made. Most of that comes from the oil industry. And then the second largest culprit is the cement industry we talked about last time, that has the downside of pulling out the big carbon sink that is in the ocean, the carbonates, and then releasing that carbon dioxide back. And we're putting about, it's a net 4 billion tons of carbon dioxide into the air each year. Industrial processes put about 8 billion in, but the planet pulls about 4 billion out. So we're net positive about 4 billion tons. There is a point, and it's been said, of like, okay, so can we rank the molecules in order of importance in terms of their effect? Which of the molecules that our book talks about traps the most amount of infrared heat? Could we rank them?
So we have like the NO, we have nitrous. or
Yeah,
NO
well,
oxide gas.
Okay, so
Which is
I
this-
did say before we switched the camera on that I'm
Yeah.
gonna more or less ignore
Yeah.
the nitrous.
Oh, wow.
The nitrous oxides, specifically the one that our book talks about is nitrous oxide.
Mhm.
Because, hey, it's already been a topic of a previous chapter, and it is at the bottom of our list of important greenhouse gases.
Water.
Yeah, all the way at the top.
Mm-hmm.
And yet, we have so much of it. And future technologies tell us things like, remember the hydrogen economy?
Yeah.
We were going to have a hydrogen economy. It didn't appear. It might still in the future. But your cars are going to run on hydrogen. And there's going to be hydrogen filling stations peppered around the country the same way the gasoline stations are now. And instead of having engines, you'll have fuel cells, and the fuel cells will generate electricity, and the electricity will run the motor in the car. Okay, and the great news is that the only thing that comes out of the tailpipe is water.
Mm-hmm.
And I was going to say, there's nothing going on, and we are not making any new water. That the water is in a cycle.
Mm-hmm. Yeah.
And so the amount that we have is the amount that we have, and we move it around a lot, but nobody's making new water.
Mm-hmm.
And in fact, even in fuel cells, the hydrogen could well be, unless it's from a fossil fuel source, which we could do, we could split and get the hydrogens out of the hydrocarbons. It's probably from hydrolysis, that you've put it in a cell itself and done an electrolysis on it and made hydrogen and oxygen, and then you recombine them later on and you get that energy back out again.
Mm-hmm. Okay.
So we take electricity, we put it into an electrolysis cell, we generate hydrogen and oxygen, and then at a later date, we put the hydrogen and oxygen back in a fuel cell, and it gives us the electricity back out again. Now, how on earth does this make sense? Well, if the energy that you used to make the first action work was from a water wheel, or a wind turbine, or solar cells, or something like that, that's free energy.
Okay, yeah.
Okay, versus, did I burn a hydrocarbon to make the electricity to separate the hydrogen and the oxygen by electrolyzing water? And then, oh, look at me, I'm so clever and environmentally healthy, I put the hydrogen and the oxygen back together again. No, you're not, because you burnt a hydrocarbon in order to make the electricity to do the first step.
Mm-hmm.
Okay. So part of the deal of the hydrogen economy is there is no pollution, there is only water.
Mm-hmm. Yeah.
Vapor coming out of the tailpipe of your car, which is the biggest greenhouse gas. Okay. I also think that if all of the cars are hydrogen cars and everybody's car is leaking water, then the roads get to be slick.
Yeah.
This is a problem that doesn't exist. Why am I worrying about it? Okay, it goes so far, far away from existing
Yeah.
that it's not worth worrying about.
Yeah, because you'd have to do a trap or something to get it recycled in. You'd have to figure out a way to literally push the water vapor out, recirculate.
We could, because people would say, this is clean water. You could trap the amount, you could be forced by some local government to trap that water and give it to needy orphans. Yeah. Carbon dioxide,
Yes.
poster child.
Yes. And methane, right?
And then methane. Now methane is not as important as carbon dioxide because there's not as much of it emitted. But if they were equally emitted, methane would be more important.
Okay.
Would be, isn't. It's a good thing that it isn't, because methane is reactive in a way that carbon dioxide is not. Primarily, methane undergoes a combustion reaction that generates carbon dioxide. So any methane that goes into the atmosphere is not coming back out, is not going to get recycled into nature as methane. We have no metabolism for that. But I could burn it, which causes carbon dioxide. This one absorbs infrared. We showed the spectra of it a couple of days ago. Has more absorbance than this. So this absorbs more infrared, traps heat more, and then, oh, good news, we got rid of it. It burned and it made carbon dioxide, which now still traps, less efficiently, still traps infrared, and then it gets metabolized. Okay, so the oxygen that's in the methane that's in the air doesn't get combusted the way that if I did it in lab, I could trap enough methane in a jar and set fire to it, and woof, it would all go in one go as a complete combustion and make carbon dioxide. Complete combustions of hydrocarbons make these two.
Yeah.
Okay. What's going to happen is, like we saw in the ozone chapter, that in the mid-upper atmosphere, stratosphere kind of thing, there'll be hydroxyl radicals. And those hydroxyl radicals that we saw in the previous chapter are the reactive source of oxygen that's in the atmosphere. And it will degrade this through a set of reactions that ultimately give us carbon dioxide, but is kind of complicated. Okay. And then, hey, there's an ozone in here.
Oh yeah, that's right.
You could even include the fluorocarbons, because those guys have polarity, but there's such a small amount of them. We're still worried about them, but not enough that they're contributors. So we're going to only deal with the top three. We will only deal with the top three. Water vapor is a massive culprit, but of course it is the most natural, and we are not worried about any process that generates water as a product, because that's good and natural. We don't really worry about it. It's evaporated water that has turned into vapor before it turns into droplets that are large enough to fall back to the planet's surface, okay? So we should probably look up particle sizes for droplets. When is their peak infrared absorbance? We should probably look that up. But they trap a whole bunch of infrared. Our book still loves to talk about microns. The peak wavelength to trap is 6.3 microns. We know how to convert that into, was it this class we converted that into wave numbers, or was that a different class?
Different.
Which class was that?
It was physical chemistry.
Did we just
did
do
it on
that a couple
Tuesday.
of days?
Yeah, we did on
Because we
Tuesday.
do those both on the same day?
Yep.
Okay, so
Because I kept getting it wrong and I kept getting frustrated, and I was like, I
looks
shouldn't do
into
this
camera and says different branches of chemistry use different units to describe things. Most wavelengths are described in nanometers. People who work in the infrared realm use wave numbers, which are reciprocal centimeters. And we know what the OH stretch is. 3.5 to 4,000 wave numbers. Okay, environmental scientists apparently love to use that wavelength in terms of micrometers or microns, which turns out to be 6.3 microns. We know what the OH stretch is in infrared because it's usually something that we want to avoid being in our product. If we see this great big band in the infrared spectrum, it means that our product is contaminated, it's not dry. For the organic chemistry world. Okay. It is the most important greenhouse gas, but of course it is natural. And we're not worried about making lots of new water, because how would that be a concern? This all fits into the fact that 96% of the greenhouse effect is natural. Okay, even if we were to make new water and new water vapor, no such a thing. All right, here's part of where this becomes a vicious cycle. Evaporation. Evaporation happens at the surface of bodies of water. So if the sun, which is where our heat comes from, heat is infrared energy, interacts with a body of water, we can make that water evaporate. That water can then get trapped in the atmosphere and build up and cause the atmosphere to warm. Warming, of course, encourages evaporation, which means that you get more evaporation, which means you get more water vapor in the atmosphere, which means you get more warming, which then encourages evaporation. And this sounds like a vicious cycle.
It was 3 million years, I think sometime just at the early start of the Triassic or before the Triassic. They had 3 million years of rain, basically.
Is that right?
Yeah. Something like, I might not have the numbers told, but it was either in the millions, it was like 3 million or 30 million years or something. It was something crazy that I was like, wow.
England has entered the chat.
Yeah,
It's what it's like to live in Manchester, England. It's like, I know what 3 million years of rain feels like.
Yes.
I have been to Manchester. It's like Seattle. It rains 320 days a year. Something stupid. Yeah. So this is what we would call a positive feedback, that the effect that you do, the cause of something makes an effect, and the effect perpetuates the cause. Okay, this is a positive feedback. There's a negative here as well, because, and our book neglects to mention this, one of the big buzz phrases that comes out of Chemistry 1 is 3 words: evaporation causes cooling. Evaporation causes cooling. What happens is that the energy from the sun is not distributed evenly amongst all of the water molecules. It is significantly more probable that one of them is the hog that gets that energy. And when it gets energy, it gets energized and then leaves the surface and goes into the vapor phase. And what that does is it robs the bulk water of the net energy that it previously had, so the water gets cold. Evaporation causes cooling. It's why you feel cold when you get out of the shower, because the moisture on your skin, your body is warmer than the room, your body is warmer than the water. Your body warms the water, which then evaporates, and as it evaporates, it takes the energy with it. Where did the energy come from? It came from the surface of your skin. And so now the surface of your skin feels cold. This is how evaporation works. That would be a negative feedback. That the cause of one thing causes an effect, and the effect strips the original cause. This is why the oceans don't boil. They don't get hot. They don't get cold. When they get super cold, they protect themselves by putting ice only on the surface, because ice is less dense than water. And so you get a protective layer on the surface. We are so incredibly fortunate to live on a planet that uses water as the basis of life. Interplanetary scientists now are only essentially looking for water as a sign of life.
Because we're the only planet so far that we've found that has water makeup.
Liquid water.
Liquid water, I should say.
There are
Liquid,
signs of
yeah.
liquid water elsewhere. I'm not sure that we've found
Yeah.
liquid water anywhere else just as yet. But like, hey, there's a whole bunch of methane on planet X. Great. But methane's a hydrocarbon. Surely that means something. Not really. No, not really. Because water is such an incredible compensator in terms of temperature. We say it in Chemistry 1. I said it just last week. Best place to live, temperature-wise, on an island.
Yeah, surrounded by water.
Because water has such a heat capacity. It takes a long time to warm up, it takes a long time to cool down. So the islands that are surrounded by water don't get hot in the daytime, and they don't get cold at nighttime.
Temperature changes.
Temperature changes, we call that a temperate climate. So without water, we probably couldn't have life.
Oregon's, or Portland, Pacific Northwest is technically temperate climate because of all the
We
water.
were just talking about this 2 hours ago. Project Hail Mary,
Oh, yes.
the new movie. One of the main crux of the scientific part of the movie is you can't have life without water. Maybe, maybe not. I haven't finished the book. Haven't seen the movie. All right. Methane. Methane is our third most important greenhouse gas. It's a component of natural gas. It's a hydrocarbon. It's a fuel. It gets into the atmosphere. Oh, it's already been on. We've already mentioned this. There is no sink for it. Not directly. It needs to be converted into carbon dioxide. And then you can dissolve it, and then you can fix it, and then you can do other things. The methane itself, because there is no metabolism for it, can live as long as a decade in the atmosphere. And because it's not building up in a concentration that's big enough that, oh, I can smell gas. Can you smell gas?
Okay.
Yeah, it's so, the whole point of gases is that they're already so far apart from each other, the individual particles, but it's going to be so incredibly dilute that it's just there. It's going to have to find itself in the right space. It's got to find where the hydroxyl radicals are. So it's going to be up in the same part of the stratosphere that the ozone activity is happening. It'll find some hydroxyl radicals and it will turn itself into carbon dioxide, and now it can join some kind of pathway that finds a sink or a way to be fixed. Okay. But that does mean that it appears on our list twice. It has its own greenhouse effect, and it has the effect because of carbon dioxide.
Okay.
All right, where does the methane come from?
Farming, agriculture, from
Yeah, so
animals.
animals are natural, and therefore animals have always contributed through carbon dioxide and methane. What's contributing to it is commercial farming or intensive farming of this acre of land, or with metric, hectare of land, used to be mixed use. It had a herb garden and it had some bushes, mulberry bushes, and had a beehive in there and a couple of trees, a couple of apple trees. Now has 500 pigs in it. Cattle, so I know a person that owns a cattle ranch. They have 1,600 acres in Mississippi. I don't know, it sounds like a lot. Do you know how many cattle they put on 1,600 acres?
I don't know.
1,600. It's
A
one cow
acre.
per acre. Now, I'm sure you can do it more intensive than that. I bet you there are places. But, yeah, about a cow per acre. But that's 1,600 cows that are in open grassland, not trees, although there are some trees, but like not trees that are harvesting the cellulose, the carbon dioxide from the atmosphere. Although somebody did the math a little while ago. Oh, I'll have to dig this up. I'll have to go look. Of does grass grow faster than trees? And because the shade of a tree means that the grass doesn't grow underneath the tree, it might actually be better to grow long grass than it is to grow a tree. That you might actually fix more carbon dioxide in long grass than in a forest. Somebody did the math. We'll have to go look that one up.
Yeah.
I'm just reminded of it right now. But anyway, the carbon dioxide that gets fixed in the grass is eaten by the cows. Cows are they're ungulates, aren't they? They have two stomachs.
Yes.
Is that what an ungulate is?
Yes.
Or is ungulate because they have split? No.
I don't know.
I've not got my phone. Look up the word ungulate. Camels are ungulates because they have split toes, or cows ungulates because they have two stomachs.
Oh, just any animal that has hooves is ungulate.
Okay.
Yes. So, well, a cow is ungulate,
Okay.
as are camels, horses, moose, elk.
They digest, so cellulose, that's a form of sugar that humans are incapable of digesting. We don't metabolize that one. We metabolize starch, but not cellulose. They are cousins to each other. They're very close cousins to each other, but they are slightly different in shape. Cows need two stomachs in order to digest that, and the inefficiency means that they burp out a lot of carbon dioxide, and they burp and fart a lot of methane. And again, somebody has done the math of how much you could look it up. How much does one cow generate in a calendar year?
How much?
Because it's a big number. And this is not a recent problem. I remember my professors talking about this kind of jokingly as when I was an undergraduate, which is a long time ago, about how some European scientists had tried to tinker with the food that the cows were eating to stop the methane production, had accidentally started making them burp hydrogen instead. And so instead of the cows being flammable, they became explosive. Yeah. So this is a really, really old problem.
A single cow typically produces 70 to 120 kilograms of methane per year.
Okay.
It says they also release significant CO2 during respiration, measuring over 6,000 liters of CO2 daily.
Yeah, but we don't know whether that's a big number or a small number, because we need to compare that to how much do you produce as a regular sized human? We don't know.
154 to 264 pounds.
Yeah. Okay.
Huh.
Plenty of methane.
Yes.
So yeah, agriculture, cattle generate methane. Is that number one on our list?
No.
No. Where does most of the methane that gets into the atmosphere come from?
Assume fossil fuels? Burning fossil fuels?
It is a fossil fuel, it's a hydrocarbon, and if we burnt it, we'd make carbon dioxide. It's the opposite of burnt hydrocarbons.
It's just that.
It's unburnt.
It's okay.
It's unburnt hydrocarbons. Where do they come from?
Brown?
Just inefficiency.
From.
Yeah. When here's the ground, here's the pool of oil, okay? There is oil down here, and I'm going to put a derrick here and drill, or I can, before I get to the nodding donkey. Here's my drill. Well, all of this liquid oil is trapped underneath some form of rock that is impermeable. But when I drill into it, the liquid comes. I can pump that liquid out. But there's also gas here. Many times. This is natural gas, which contains methane. What am I going to do? I'm here to pump oil. Nature's giving me methane. What am I going to do with it?
I would like you to be able to redirect it back to us so we could use it for natural gas, but it's going right out into the environment.
We're probably just venting it.
Yeah, it's just venting. So when you drive past the drills, you can smell it.
Other times, if you ever see out at sea, more often, the big rigs, they have a flare. They're pumping the oil out. There's gas mixed in with it. Let's just flare that off. And if it's a yellow flame, that's incomplete combustion. Complete combustion comes with a blue flame because you're going to mix it with oxygen. The deal with how this is burnt is if you just have a tube that is a chimney and the gas comes in and you set fire to it, that flame is yellow. You drill a hole in this chimney, it lets oxygen in, and the oxygen and the gas mix together before they catch fire. That's now a blue flame. Blue flames, complete combustion, carbon dioxide and water. Yellow flame, incomplete combustion. Incomplete combustion means the fuel also escapes.
So you're having CH4 escape right out.
Yeah. Like anytime that, good grief, you're looking at the news. One country is bombing the other country's oil fields as we speak. There's hydrocarbon absolutely everywhere. Yeah. And then in retaliation, the other countries are now bombing that country's oil fields as well.
In their tankers, that's right, oh yeah.
And the tankers in the Straits of Hormuz, the whole region's oil is on fire. Yeah, that's where the methane comes from. It's just mostly lossy. It's from being inefficient. It's a gas. This is a solid. When I put it down, I can rely on it being there later on. If I have a liquid, I have to put it in a container and then probably have to cap that container and in order to be fairly certain that it will still be there later on. Gas is a completely different problem. If I don't put it in an airtight container that doesn't get tampered with, then I have no belief that the gas will still be there later on. This is why, while our general chemistry textbooks are full of gas equations, because the math is simple and the chemistry is simple, we don't have labs that deal with gases because they're too difficult to work with. Every time you work with a gas, when I take the lid off to move this gas from this container to that container, I'm going to lose it. Yeah, it's just from being inefficient. If we're going to prioritize where the methane comes from, just lost from fuel. The fuel industry just not being efficient. Then agriculture. I'm just saying cattle because it's the big one that people talk about. And then an odd one that in the West we don't think about.
Oh, is it, it's more agriculture then, it's
It
different,
is.
it's, rice paddies.
Rice.
Yeah. Either that or palm oil, palm trees, but
Oh, okay.
I might have just went down another rabbit hole though.
And then, do I have anything lower than rice? Oh yeah, yes I do.
Oh, okay.
Let's do the last one. Landfill. Hey, my trash pickup is tomorrow. I put the trash out on the curb. The guys come. If they see me, they wave. I wave back. They're nice people. And my trash is gone. Bonus. We don't have to worry about it until next week. I have no idea where that trash goes. Not a clue. They take it somewhere and they bury it. And everything that's in that trash is now on the clock, ticking. It is going to decompose. If I had an apple and this is one of the things, like, hey, if you are driving in your car and you throw a cigarette butt out of the car and the police pull you over for littering, you get a ticket. Okay. If you are driving and you pour the remainder of your water bottle out of the window, do the police pull, and then you pull the bottle back in, do the police pull you over for littering? No, because water's not litter. If you tossed an apple out of your car, do the police pull you over for littering? I think it's situational.
Yeah, I think that's
Like,
situational.
if you tossed an apple onto the sidewalk at the Domain where everyone is shopping, that's littering.
That's litter, yes.
However, if you're driving down a country lane that's wooded on both sides and you toss your apple core out,